You guys can hear me?
Yes, sir.
Okay, so I hope the others will be joining in. As of now, you are 1, 2, 3, 4, 5, 6, 7 of you are there. So those who are interested, for them, I'm sharing the screen, and you can see others will join in, I guess. In the meantime, so you can see my screen. Vishal and others, they know. Those who don't know, this is the website for AICT training and learning. So this is called the AICT training and learning, or Atal Academy. So under this Atal Academy, so whatever is a relevant area, if you are from statistics, anybody is there? Statistics? I guess no. And electrical. No one yet. So others like electronics, I think two or three of you are there, isn't it? And IT, Ananda and Hillary is just joined in. So Vishal is there from MCA. Vishal and others, they know. Here in this AICT training and learning website, you have, if you have not, wait, just wait for them to join in. Now they are joining in. Okay, so this is the website of AICT Training and Learning. So those who don't know, you can have a look here, and here there is a list of workshops, whichever is say here there is a list of workshops. You can sign up in case you don't have an account here, or you can log in with your Gmail account. And those who have already done some AICT training and learning or ATAL workshops, you can get your certificates here by verifying the same email ID. So here is Jayant sir's listed workshop, Introduction to Quantum Computing, from 8/11 to 12/11. So once you register and you log in, you get it. And the next workshop is from 7th February to 11th February. So in case those who are say interested in doing the advanced one also, they can do it in February. Presently from 8 to 12 of next month, that is the second week of November, we are having this. So up to say this week, or maybe up to next week, you guys can log in. And it is not that you have to do only our workshop. You can attend as many workshop you want, up to 4 if per email ID, if it is, but you have to, if you want to do it seriously, you need to give time. So respective areas also there. So you can see so many workshops are there. So number of listed workshops FDPs planned are around 1500 workshops, and already out of that 900 have been completed already. Okay, so you guys, whether you are from statistics, electronics, electrical, IT, or computer applications, whichever department you are from, and say you are working on some project, say somebody from electronics is working on antennas, and somebody from electrical is working on drives. So there are smart drives and other workshops. You can have a look. For this academic year, it is nearly over, because 1500 workshops, 900 already over, 900 plus. So you can sign up if you have not yet signed up, and relevant to your master degree project, you can do one or two workshops. And presently our department is organizing two workshops, one both in quantum computing. So if you are interested, you can join. You were not there 2 years back when Bishal and others from MCA group, they were there in the first year when we organized this offline workshops on quantum computing, AI, machine learning, and data science, as well as two international conferences, and just before the corona started. So Only the MCA batch is of 3 years. This is the final 3 years batch. So they were there during 2019-20. You were not there, so you didn't attend the offline ones. So these online ones are going on. So if you are interested, you can sign up here, and in case you already have a login ID, you can log in here. Okay. So I hope 13 of you, 13, 14 of you are here. So statistics, someone is there? Statistics, somebody is there? Okay, no one from statistics is there. Other departments, I think they're there. Electrical, I think somebody is there. Electrical? So electrical and statistics means people are not there. So should I start off, because this problem that I was planning to take was more statistics oriented. I was planning to finish up by 11. Less than 50% of you are there.
सर मैं स्टैटिस्टिक्स से ही हूँ.
Okay. So what about the others? Electrical? Electrical, anybody? Because electronics, IT and MCA I can see. Jitesh, you are there, I guess. Jitesh is there from electrical, I guess. Anyway, so I'm starting anyway. So yesterday I told that we will be say discussing a problem. So today I'm discussing the problem. So here the problem that I'm discussing is considering the domain, like say I'm going home and I want to know if somebody in my family is at home before I go. So uh, before that I want to give some information based on which we'll be arranging the problem. The first thing is that uh, my wife leaves the house often, but not always. Whenever she goes out, she turns on the light. Okay. But sometimes she, even if she is inside the house, she turns on the light, outside light, if we are expecting a guest. Okay. That is one. I'm just giving the scenario. Number two, when nobody is at home, the dog is often left outside. Okay. So dog is outside when nobody is at home. But again, if the dog is having some stomach problems, then also it is left outside. So the dog is outside in two cases. Either it is having some stomach problems or nobody is there at home. Okay. And the light is on in the outside light is on if my wife leaves the house or she is expecting some guest. And if the dog is outside, I will probably hear it barking, though it might not bark also, because that barking that I can hear, it may be of my dog or it may be somebody else's dog or say outside stray dogs. Okay, getting the scenario. Here we are taking some probabilistic model. So Geeta is from statistics and you know probability well. I'll be discussing later on. I'll just put some values and we'll do, and you can change the values. The solution will change. That is a different thing. So presently what I'm taking 4 scenarios. The first scenario is outside light is on. So outside light is on in case of 2 scenarios. One scenario is my wife is expecting some guest, or number 2, she is outside. So either she can be inside and expecting guest or she can be outside. In both cases, light is on. Then if nobody is at home, then the dog is left outside. But sometimes when the dog is having some stomach problems, then also the dog is left outside. because otherwise it will dirty the house. Okay. The third case is if the dog is outside, I can hear it bark, but sometimes it may be that I am hearing somebody else barking also. Okay, clear up to this? So let us give this boolean random variables here. O, everyone is outside the house. L, the light is on. D, the dog is outside. B, the dog has bowel problems. And H, I can hear the dog barking. Okay up to this?
Yes, sir.
So we are defining 5 variables: O, L, D, B, H. O is for everybody is outside, nobody is inside the home. L, the light is outside, light is on. D, the dog is outside. B, the dog is having bowel problems. And H, that is, we can hear some dog barking. Okay. So with this particular thing, let's go for the solution. The first thing is H is directly influenced by the dog, because H means if I am hearing somebody barking, so obviously it will be the dog. So it is conditionally independent of L, O, B, and D. Light is not related to hearing the bark. Outside light on this everyone is outside is not related to the hearing of the barking. Then bowel problems of the dog is not related to the hearing, but it is conditionally independent. Then D is directly influenced by what? O and B. The dog is outside only if everybody is outside or it is having bowel problems. So D is conditionally independent of L and O and B. L is light, O is outside, and B is bowel troubles. Okay. Number 3, L is only directly influenced by O. Light is on only if everybody is outside. So L is conditionally independent of dog, house, bowel, hearing and bowel problems, and if everybody is outside. And the last one, O and B are independent. O is everyone is outside, and B is the dog's problems. So dog's stomach problems is not at all related to whether everybody is inside or outside. Okay. So based on the above, what we'll be doing, we'll be designing a Bayesian net and representing these causal relationships, though it may not be the absolute, but still we'll be making the connections. So this is the information we have, O, L, D, B, H. I have kept it because we'll be using that. First thing, now I'll go top from bottom. Here, instead of going from 1, 2, 3, 4, I'll be making 4, 3, 2, 1. Okay. The first is what? O and B are independent. So I insert O and B. So these two are independent objects, O and B. Clear? The fourth one, I'm taking the fourth one first. Okay. I hope you are getting it. If you're not getting, I'll be going back to the initial problem. Because later on we'll be calculating the probabilities. Because as of now, I have not defined the probabilities of the different objectives. Okay, then we'll be going for the conditional probabilities. Okay up to this?
Yes, sir.
So O and B are independent. Second is light is directly influenced by O. Means if everyone is outside, then the light will be on. So L is conditionally independent of D, H, B, and O. So directly O and L. So O influences directly the light being on. Okay, this is one of the issues. Second thing, D means the dog is outside is influenced by two cases. One, if everybody is outside, or the dog is having bowel problems. So hence D is conditionally independent of L, O, and B. Okay. The fourth one is hearing of the barking is influenced by dog only. Only the dog can influence the hearing, whether it is my dog or it is somebody else's dog. Hence H is conditionally independent of the other four. Okay. So we have got a graph. What we'll do is that we'll assign some probabilities here. Okay. So this is my graph DAG. So giving some quantitative values, what we can do for each root, because here root means the root nodes and we have the parents. So node without parents, the prior probability for any random variable, whatever is there, we'll actually give some conditional possibilities and the combinations and other things, and we'll be putting the values. So we'll be making a conditional probability table for each thing. Now here, whatever I'm using is just logical values which I am putting. You can change the values, but obviously don't make that illogical. You can put any logical way, because something 0.6 or 0.5 is nearly same. Only the values will change. So here we have taken this O, B, L, D and H. Out of that, what we have done? We have taken PO, probability that everybody is outside, is 0.6. Okay. And bowel problems, probability of the dog having stomach problems is 0.3. Similarly, light on, because everybody is out, is 0.3, and light on because we are expecting guest is 0.6. Now you can change these things also. Okay, no problem in that. And probability, here you see dog and everybody, dog is outside because everybody is outside, and you hearing barking is for with respect to the bowel problems is 0.05. DO B naught is 0.1. DO naught B is 0.1, and DO naught B naught is 0.2. So we have taken all the possible cases. You can consider as DOB, DOB bar, DO bar B, DO bar B bar. So these are the 4 cases that you can have here. And the last one is hearing the barking. Now it may be 0.3 because of my dog and 0.8 if it is not my dog. Now here you don't see, here we are not making it always 1 here, because my dog and not my dog, these are actually again conditional probabilities. So here we are just assigning some random values. We are not keeping everything equal to 1, because here these are all separate entities. O is a separate entity, then B is a separate entity, L is a separate entity, D is a separate entity, and H is a separate entity. Okay. Here we have taken 2 conditional probabilities, H for D and H for D naught. So H for D naught is 0.8 and H for D is 0.3. Okay. Though it is, you just directly don't go for adding them up, because if you add up, it will become 1.1. Okay. Because these are conditional probabilities. Because here you may not know that this dog that you is barking is yours or somebody else. So you can assign different probabilities here, and based on the data analysis, you can put the probabilities. Here I'm just giving a problem with this set of probabilities. Now we'll be going, these are just to get a numerical value. If you don't put this, no problem. You can directly use the H and D and H and D bar kind of thing. Here to avoid the bar thing, I am using this particular thing, so that when you write, if you this negation, I am using with a this mark instead of bar. The class was to start at 15, okay, so that I can finish it by 11, because our MCA fifth semester are having other classes also. So I don't want to occupy 2 hours of their normal routine. Okay. So next, going here, you see here we have 5 different probabilities, O, B, L, D and H. So based on that, we have in general 10 different probabilities, means O bar, B bar, L bar, D bar, H bar. Now all these that are there, so there are 2 to the power 5, so 32 probabilities. Okay. So total we have 32 different probabilities are there. So here we are taking a few of those 32. Now, because of the conditional independence of the various variables, we can have different entities coming up. So 2 variables that are not directly connected by a arc can still affect each other. Now you see here, this H and D is connected, P and D is connected, O and D is connected, O and L is connected. So here I have taken only the DAG connected probabilities, but there are some other cases like bowel problems of dog and the light outside may be related also. We do not know about it. It may be because the dog is outside and because of these bowel problems, the light is left on. So we don't know about that. So that's why there are 32 different probabilities, but here I am taking only the directly connected ones. Okay. And these not connected ones also can affect each. No. So directly they are not connected, but again they are dependent on each other. So for this Bayesian net, we can say read off the conditional independence relations, and some of them will be represented. So each node, if you consider, we have descendants and we have parents. So these are the descendants and those on the above. So O and B are the parents of D, and H is a descendant of D. So it is something like grandfather, and this is the grandchild. In between, you have the father, mother here. Okay. These ideas were later on used in genetic algorithm and those things. I'll be avoiding that. Any of you who has studied genetic algorithm? GAGP, genetic programming, genetic algorithm, gene expression programming. Any one of them? In your UG also as an elective paper or something? Any one of you? Okay, so many of them are applying genetic algorithm, genetic programming there. If you are interested in your different application areas, you can also put them. And those are again soft computing ideas which are used. So H is conditionally independent of B and O and L given D. So H is connected only to D, but O, L, and B are affecting it indirectly. So probability of hearing with respect to your bowel problems, dog outside, people outside, L is equal to HD because the others are independent, only the dog is dependent here. So this is equal to this because other B, O and L are not correlated with H. I hope this particular probability, conditional probability is okay with respect to the graph, with respect to the DAG diagram. Okay.
Okay, sir.
Okay. So building the Bayesian net, what we have is, as per the Hackerman's definition, is to construct a Bayesian net for a given set of variables. We can draw arcs, that is the DAGs, for the cause variables to immediate effects. In almost all cases, doing so results in a Bayesian network whose conditional independence implications are accurate. So this was given by Hackerman, say 20 decades, so 2 decades back. So formally, if we go, first, what we have to do is to identify a set of random variables for a given problem domain, like we have done for B, O, D, L, and those things. Then choose ordering them x1 up to xn. We'll order them. Then for I equal to 1 to n, what we have to do? We have to follow a set of steps and we have to repeat it again and again. What are they? Add new node. For every new thing, we'll be adding a new node. The parents xi to be minimal, and based on them, you will already add the nodes one by one, and we'll have x1, x2 up to xi minus 1 for the parents. Because why I minus 1? Because 1 will be the from 1 to I minus 1 means here we'll be going ahead till the last one. oh, sorry, just a minute. It will be n minus 1. I have to make a change. So this is x1, x2 up to x n minus 1. Okay. I is in general for the different, and the last one will be from, we have to avoid the last one because one will be the parent. And we have to add the directive arc for the parents xi to xi. And based on these, what we'll be doing, we have to define the different probabilities based on which they will be connected. Okay. So based on this algorithm, what we can infer is that there is not in general a unique Bayesian, because no Bayesian network will be unique by itself for any set of given random variables. Secondly, but what we can do for this particular thing is that all of them represent some information, and from any net you can construct based on the joint probability distribution. The best net, if you want to construct it, what you can do, each variable comes before its children, because whatever correlations are there, the parents come before the children. So the first node should be the roots. That's why what we did is that we went from the number 4 to number 1, and then we constructed. The parents were coming last when I was discussing, but when we had drawn the parents first, and then we had gone ahead. I hope you have seen that. And the last one is the algorithm will not construct a net that is illegal, means we will not be doing anything out of the box. Okay. So for any joint probability for Bayesian net, what we have to do is, say for example, I take a particular case, compute B means bowel problems, O, this one not O bar means not everybody is not outside, D is dog is there outside, L bar is light is off, H is you are hearing barking. So we want to solve this particular problem where bowel problems is yes, people outside is no, dog outside is yes, light is off, and you are hearing some barking. So if the dog is having bowel problems and you are in the room, the dog will be outside, the light will be off, and you are not expecting guests, and you can still hear the barking. Now that barking may be from outside dogs, and it may be your dog which is say barking because it is having some stomach problems. Okay. So in this home domain, you can solve any kind of problem. So this is one of such problem. So this is the probability thing that we had defined. So we know that P O bar D L bar H is can be rearranged as P H. I am putting H and L bar together. D here, O bar and B. I have just rearranged it, nothing different. You can see here, these are rearranged, just rearrange. H is here, then L bar is here, D is here, O bar is here, and B is here. I have just rearranged from top to bottom to bottom to top. So first thing, using product rule, what we can do, we can apply for hearing L bar, D, O, B, and P for L, D, O, B. Okay. So for this, what we have is we have this H means hearing with respect to this, and the probability of this L bar, D, O bar, B without H. Okay, using product rule. So when we know that this hearing is only dependent on the dog, so the other terms we can remove. So we have removed the other terms. So it is only PHD. Okay, H is hearing and D is this, because we are hearing only the dog. So whether it is my dog or it is outside dog, that is different thing, but it is hearing the barking is related to the dog and not anything else. And this is as it is, using the conditional independence of H with L, O, B given D. Next, coming to the product rule here. Now this one is as it is. Now I expand this one. Here I put L bar. Now we have D, O, B and D, O, B. Again the product rule is applied. Now you see, you have conditional independence of L. L is connected only to O. It is not connected to B and D. So this will become L bar O bar. So you have L bar O bar only here. The others are removed. And D O bar B. Now L bar O bar is here. Now again we apply the product rule in this term. So D O bar B and P O bar B. Applying product rule. HD here, P L bar O bar, PD O bar B as it is. And this one again we apply the product rule. So P O bar B and PB. PB is probability of barking. So after this, the next step, these are as it is. Only change is here because O is not related to B. So P O bar and PB. P O bar B is not at all there. So it is same as P O bar because of the independence of people outside and the bowel problems. So now let's put the values. PHD. HD is 0.3, so I have put 0.3. P L bar O bar. So L bar O bar is what? L bar O bar is not given. So we have L O bar. So it is 1 minus 0.6. L O bar is 0.6. So L bar O bar is 1 minus 0.6. Then P D O bar B. Now P D O bar B is here. So it is 0.1. So I have put 0.1 here. And next P O bar. Now O bar is not given. P O is given is 0.6. So P O bar is 1 minus 0.6. And the last one PB is given as 0.3. I hope it is clear, this part. How we are bringing it down step by step. Clear?
Yes, sir.
Anybody, any problem regarding this? How we have broken up the whole thing? So what will be the final value? Anybody? You can calculate it. 0.3 multiplied by 0.4 multiplied by 0.1 multiplied by 0.4 multiplied by 0.3 again. Statistics guys, is that okay? Because you are more expert than me in this particular probability and statistics, because you should be teaching that particular soon. Once you are out, you will be teaching this probability and statistics. Anybody who has come up with the value? I have already put the values there. You just give me the value.
Sir, it is 0.001.
Yeah, I have done it the whole decimal place. Anyway, same thing. So here, what we are doing here, all the numeric values that are there, because we know that P A bar B equal to 1 minus P A B conditional. So we have applied this for those missing probabilities and we have calculated them. You have seen this for this one and this one. For two terms, we have done 1 minus 0.6 and 1 minus 0.6 because we didn't have the direct probabilities. So we have used the reverse logic. So I think you know that. So there may be two ways, as I told in the last class. One is the top-down approach and one is the bottom-up approach. So I'll discuss first the top-down approach. So if I go by the top-down approach for the Bayesian net, if you here in the top-down approach, what we do here, as it is causal or top-down approach, we from the evidence we come to the query. Means top-down means I have some evidence. Based on that we find out what is the query. So this is called causal inference or causal arc. So for example, I have a problem PDB. What is the probability that my dog is outside when it has bowel problems? Okay. D oblique B. D is for dog, B is for bowel problems. So probability of D, dog is outside, for bowel problems is P D conditional B. And the question here, the query here is, what is the probability that my dog is outside when it has bowel problems? So let's calculate this one. So here we'll apply the product rule and marginalization. I hope this part is okay. PDB, D conditional B is equal to DB divided by PB, product rule.
Yes, sir.
Okay. So then as we go ahead, what we have? PDBO, DBO means now it is outside. And DBO bar is, it is not outside, divided by PB, means bowel problems. Means the dog for bowel problems is outside, or the dog for bowel problems is not outside, divided by the probability of bowel problems. So we are marginalizing this PDB. Now, you know here is that this PDBO divided by PB. So this PB is divided in both. We have separated the terms. So PDOB, this is DOB, and PDO bar B. So we have two terms. Second part is we can apply the conditionalized version of the chain rule, PAB, this chain rule. So we can apply the chain rule here. So once we apply the chain rule, what happens? This DOB will become D conditional OB and POB outside for bowel problems, and D conditional O bar B and P O bar B. Now as O and B are independent of the network, so POB is equal to PO, means outside and bowel problems is, you can see here, are independent. So similarly, PO bar B is also PO bar. So we can replace them here. So this becomes PDOB, okay, but this becomes PO, and similarly this becomes PO bar. So now we can put the values. PDOB is already there, 0.05, and PO is 0.6, and PDO bar B is there, 0.1, and PO bar is 1 minus PO, that is 0.4. Okay, so based on that, this probability is 0.07. So here what we have done, we have rewritten the goal conditional probability. The query variable is Q, and from the evidence we have found out the query variable. Secondly, what we have done is we have re-expressed the joint probability, and thirdly, we took up it in the Bayesian net for the required values. So this is the top-down approach. Similarly, we can have a bottom-up approach or the diagnostic inference, what I had discussed in the yesterday's class for the liver cirrhosis kind of thing. Means when we are getting the probabilistic model, we have some instead of the query and evidence relationship is reversed. So if we have a reverse relationship, it is something like a diagnostic inference. PQE here. So if there is our query to finding out the evidence. So from the query, now here we are finding out the evidence. Okay. So it is just the reverse process of what we have done in the last one. So from the symptoms, we are inferring the cause, just like we did for the liver, that is bloodshot and this jaundice. We found out whether it is a pickle liver or not. So we have this abduction rule of first order logic. Anybody any idea what is that abduction rule? Statistics guys? Induction, abduction. यहाँ पे abduction kidnapping नहीं है. Statistics students, what is the abduction rule for first order logic? Do you remember? Anybody?
No, sir.
Okay. One is the deduction logic or deductive logic. So here what we do, we lead down towards the conclusion. Second is the inductive logic, where we lead into the conclusion, and this is normally true. But in abduction rule, what we do is something like what doctors do. They come out with a, let's say, probably guess or something. So that is called the abductive logic. So you lead away and we guess the conclusion. Okay. तो फिल्म आधा देख लिया, तो अंत में तो हिंदी फिल्म में सब हीरो जीतता है काइंड ऑफ थिंग, सो दैट काइंड ऑफ गेस. ओके, अभी कोई डायरेक्टर अगर आउट ऑफ द रूल बना दिया कि लास्ट में हीरो को मार दिया, विलेन को जिता दिया, दैट इज अ डिफरेंट थिंग. बट नॉर्मली that is the normal system in Hindi films, so you can apply a abductive logic there anytime. So here we have the home domain where we are computing p b bar d bar. B bar means no bowel problems and dog not outside. So if the dog is not outside, what is the probability that it has bowel troubles? Means अभी डॉग तो बाहर में नहीं है, लेकिन घर में उसका पेट का प्रॉब्लम होगा तो क्या पता. ओके, so for that, first we'll apply the first Bayes rule. So P probability of B bar D bar equal to probability D bar B, PB and P D bar. So that is one thing. Second thing is that if we look up in the Bayesian net, what we have is PB bar 1 minus 0.3 is 0.7. Second is, next we compute this PD bar using the causal inference. So P bar is just the reverse of this 0.3 is 0.7. So here we get L bar B. L bar B means L and this B. They are not at all related. So what you have to do? You have to take it as P D O are not on and bowel problems are not there. So these two have to be correlated here. So here what we have to do is this D bar O. D bar means dog is not outside. O is people are everybody is not is outside, and B bar. So if everybody is outside and dog is not outside, it may not have bowel problems or it may have bowel problems. These two cases are taken into account. So based on this, we are again going, and if anything is not correlated, we will actually reduce it. So D bar O B bar, you can see here D bar O B bar. So now D bar O B bar is not there. So what we will do is we'll take the reverse logic. 1 minus 0.1 is 0.9, and PO O is here 0.6. So 1 minus 0.1, it is 0.9, and here it is 0.6. These two are multiplied here, and D bar O bar B bar. Now D O bar B bar is there 0.2. So 1 minus 0.2 is 0.8. Actually, I didn't have space, otherwise I would have written 1 minus 0.2. Anyway, so you have 0.4 here for the other one, that is 1 minus PO. So it is 0.86. So this B bar D bar here, which we had here, is actually equal to this 0.86, that is L bar B bar, multiplied by 0.7, that is P B bar, and PD. Now this P D bar we have to calculate, because for D bar, P probability of D bar I don't have with me here. So in the second step, what we do, we have to calculate this D bar, means dog is not outside. So for this P, there is bowel problems, dog outside is equal to this. So P barking is 0.3 as per the Bayesian net. So we can find out this in this way. D bar B is equal to this. As we go for the second step, so we are having this P D bar O and B with POB and P D bar O bar B. So we have the values of these. Because this is not related, so O bar, this is not related, so O, like this we are having, just like we solved earlier. So 0.95 for the first one, because 1 minus 0.5 is 0.95. Then PO is 0.6. Then it is 1 minus 0.1, it is 0.9. And this PO bar is 1 minus 0.6, so 0.4. So it is 0.93. So this P D bar barking, sorry, bowel problems and dog not outside. If we put here, we can see here, this is 0.93, this is 0.3. So it is 0.279 P D bar. So still we are stuck in P D bar. Okay, up to this.
Yes, sir.
So as we go ahead, P, no bowel problems and no dog outside, plus P, bowel problems and dog outside is 1. Means uh, with without bowel problems, dog not outside, and with bowel problems, dog not outside. So in both cases, the probability of these dog not outside is 1. Dog not outside probability is 1. So based on that, with or without bowel problems, so this is 1. And we have this 0.602 PD bar, 0.279 from here equal to 1. So PD is equal to 0.8. You can take the PD bar common, and based on that, PD bar is equal to dog not outside is 0.881. So once you get the probability of dog not outside, so P B bar D bar we can put under this 0.602 which we got earlier, divided by 0.1, it is 0.683. So this is a bit lengthy process compared to the earlier one, but anyway, based on the complexity of the problems, now here we have more number of variables on the top and less variables in the bottom, so that it might be an issue, but anyway, you can solve any of the problems in this way. So to summarize, what we have done in this particular reasoning under uncertainty is, first, you have studied the methodology for building a Bayesian net. Then this Bayesian net is compact and it does not require any exponential storage and other things. It goes step by step, and this is very important because otherwise, if you require exponential storage and if you have more memory requirement, then it will create a problem. Next, if we compute the probability of any given assignment for the true values, and we go on computing step by step, so computation is obviously fast, linear, and the nodes are going there. So P, Q, E1, E2, EK, these are the events or evidences, and Q is the query. So based on that, the different evidences are there, and based on that, we can solve the query, and we can enumerate the matching cases of joint and different variables. So in general, what we have, Bayesian network is normally a NP hard problem. NP hard and NP soft. Anybody has heard of this kind of problems? NP hard and NP soft. NP hard, NP soft. So these are tree structures. These are used in computational intelligence and other things. You can solve different problems based on these networks, probabilistic models and other things. And nowadays, any application that you want, if you can build a probabilistic model, you can get a DAG for the Bayesian net and solve it. So you have belief networks or neural network based belief networks are also there. Neural network I'll be taking up later, and there I'll be discussing that. So up to this, if you have any query, tell me.